population is at 51.7% female.
Well, there's also those countries that tend to do away with the females.
Fortunately, China has revised its one-child
That
policy.
would lower the female population, not increase it.
Not increase it. So think about all those females if they did.
It's scary enough as it is.
I know.
Women are scary.
We are.
Just ask my ex-wife. What?
I didn't say anything.
Oh. Who did?
You just don't want to get on her bad side.
My ex-wife? I don't even know where she is, so.
That may be a good thing.
Oh, it's a good thing.
Well, then just
I don't
hope
know
she
where one
doesn't
of my
watch this
exes
video.
is either.
Then just hope she doesn't watch this video.
She's here. Schizophrenia is a wonderful way to.
Yeah, that's what my daughter has, so.
The one you're bringing back?
Yeah. The one who's pregnant, yeah. Who doesn't want to take her meds, yeah, that one.
Oh, wow. So all those hormones would just be a real.
That's what I tried to explain to I'm like, yeah, not including when the baby's here, the lack of sleep and all that kind of stuff is gonna really make her way worse than she is now. She lives in kind of a la-la land anyway. Her realities are a little off. She's super paranoid.
Brain got both delusions of paranoia and delusions of grandeur. No, I'm sorry, persecution and grandeur.
I've heard so much of her conditions.
God was going to give reunification theory to bring himself back into the field of physics. But he did it right away, so he beat her up. You can love him more if almost something like that.
Oh, I know. Her father gave up because he
Was
almost
that
killed
way
her.
you can like sign on through Wi-Fi and it's you're not a guest?
They're saying to use the guest right now.
Just on you guys?
Yeah, because the other one's screwed up.
They're all screwed up.
Yeah.
I keep going back and forth between both of them.
Are you on a PC or your handheld?
Yeah.
On the PC, it tries to register your MAC address, which is nice for all those people that have Windows 10
Yeah.
that defaults to a random MAC address for anonymity.
Defaults to.
I think it does, or it asks you early on if you want to do that. Which of course you do because anonymity.
I've asked them to fix the internet in this building, I don't know how many times, because there is no internet in this building.
Well, he's getting Google.
Oh.
You have to bounce back and forth between all of theirs. It's never a very good internet.
On the guest last week, I uploaded the video tape in about
Took 20 years.
4 minutes.
Really?
Yeah, at home it would have taken overnight.
It just comes and goes. It's just weird. There's no cell reception down here, so it's not like I can connect to that.
You calls all the time.
Down
Yeah,
here?
I've got
Really?
full bars on full G, but I'm 18G.
No, maybe that's why. US Cellular has nothing down there.
I'm Sprint. I have a friend for pretty good connection down here. Yeah, 3.5.
Really? God, I have like less than 2. That'd be crazy.
All right.
Yeah.
Let's go ahead and get started,
Just
shall
like amphetamines.
Well, yes, amines. I don't think amphetamine is actually going to be one of the specific examples, but yeah.
Shots.
We'll have barbiturates in there. Close enough.
Can you teach us how to make it in the back of cars?
How to what?
Nothing, I didn't say anything. But I think as part of our education, you should bring in some meat.
Oh. I don't have that much of that left at home. We drank most of it. And I have not taken the time. I could say thanks to you guys, but I'd lie. So I started another batch. I really should.
Go get a bunch of fruit.
Oh, I have it. I got a can of raspberries and a can of blackberries, and 12 pounds of honey. So I've got everything I need except the yeast to get one started. And the yeast is just driving up to warts and all, and paying $15.
Really?
There's a brewing place just north of town on something, not 63. But it's a guy who works at the university of Mizzou, and so it's open really weird hours, like 2 or 3 hours in the evenings, and then some odd hours on the weekends. Because it's
That was
He's like
adorable.
a cat. I know.
There's a sort of a head shop on Wilkes Boulevard that sells some brewing.
sort of a head shop.
Sort of.
It's a head shop, but it also provides things like Kratom, which my roommate uses.
Is it a creative nicotine and/or smoking establishment?
It's a head shop. They sell bongs.
Yeah.
They call them water pipes.
Right. Except I don't know, because the last time I was there was like a year ago, and they told me that they were getting rid of their brewing stuff. So it's still named as a
small
brewing
section.
company.
No, it's just a small section,
Okay.
and then there's like a garage sale off on the side.
They probably don't have the yeast that I like to use though. I like to use a liquid mead yeast as opposed to a brewer's yeast. Gives it a nice secondary metabolite, gives it a bit more of a floury flavor.
There's a guy in the Shire that just makes so much meat in hot glasses on it.
All right. Let's talk about amines. Indigo uses a blue dye. Get that from, I think it means tropical plants, not topical plants. Plants that grow on your skin. Indigo tinctoria. It's a blue dye, which is neat because blue actually, chemicals specifically, that give off light in the blue range are relatively rare in nature. Which is an interesting thing if you wanted to Google why blue is rare. We've got some YouTube videos that explain that. What's that?
Well, it's just tropical, but Middle Ages, they had entire regions of Europe devoted to growing indigo.
Yes,
For
but
the
that,
career, whatever that trade is.
for dyeing of clothing, you mean?
Yeah.
Yeah. I just don't know if topical is the right word here. I mean, it could be a tropical plant that's grown in other areas too, but I don't think topical. I've not heard of topical as a description for plants. It's not really that important because it has really nothing to do with the structure, but this is the interesting thing about this. The reason, and we haven't really had time to talk about this, and I kind of want to mention it because it's cool, and I mentioned it in passing when we were talking about the whole cabbage pH thing, right? So this is a benzene ring right here, which means all of these carbons are locked, right? Onto the same plane, okay? This is a double bonded carbon, which means that it is also locked in the same plane, because remember, whenever you have a double bond, you have a planar orientation with a 120-degree angle between the three atoms. So that means that since that is in the same plane as all of those, that one is in the same plane, and so is that one, which means that this nitrogen is as well, which means that that carbon is as well, which means that that carbon is, which means that that one is, which means that all of these are. And so what that means is that all of this electron density, the double bonds that lock them in a plane, the electron density here is this big cloud of electron density around this, right? You have a big cloud of electron density around this. This is all in one ring with double bonds stepped off, so you have a big cloud around electron density here. It follows through like this. We have our pair of lone pair up on top of that, so it can link out around that, which means that all of this flows around as well. And about the only guys that don't play along are those two hydrogens hanging out. So what you get is a whole bunch of electron density on the top of this molecule, and a whole bunch of electron density on the bottom of this molecule that looks exactly like that. And the reason why that's all important is because when light is coming in, the wavelength of light that is absorbed and therefore reflected, which things are absorbed and emitted out, is dependent upon the amount of this that you get. And so the longer the chain that you have, the lower energy release you're going to get. And so when you look at Roy G. Biv, red, orange, yellow, blue, green, right? So that, then violet, the longer the chain that you get,
the further, the deeper into that you're going to get as far as the amount of energy that is there and that is then reflected when it's given off. So the way you get dyes, the way you get molecules like this, is by getting a whole bunch of electron density that's all connected. But if you broke that down so that this cloud wasn't shared with that cloud, that would be colorless. Because this is now a much shorter chain of electrons that can share and absorb that energy. So that's how those pH indicators work, is by having something that under a certain pH, it's free to rotate, but under another pH, we change the charge of a nitrogen atom or something like that, and that locks it into position, which links two different electron clouds together, and suddenly it has a color. Because the energy that's absorbed and then emitted is emitted at a lower energy level because of that longer electron cloud to share that energy before it's emitted, and if it gets low enough, it'll actually enter into the visible light spectrum. And the longer the chain, the deeper that emission becomes, the deeper into the visible light spectrum. So that's what dyes are. That is why this molecule of indigo has a color, because of the large amount of electron density there is that's all linked together in this molecule.
So the 2, 2 prime, is that the indicator that it's a trans? The 2 prime?
Where do you see? Is that from the nomenclature online?
Yeah.
For indigo? I see. It could be because, yeah, the trans, the fact that our ammoniums and oxygens are opposite, but I'm not sure. I'm actually not sure about that. It's certainly deeper than what we need. We're not going to try and actually name the chemical formula of this. It's just indigo. But we are going to talk about amines from a simplistic perspective. So, amines are chemicals that are derivatives of ammonia and or have a nitrogen in them, a nitrogen atom. We have one or more hydrogen atoms around the ammonia replaced with alkyl or aromatic groups. So here we have an ammonia functional group, or an amine functional group, that has had all 3 nitrogen replaced with alkyl groups. A propyl group on one side and 2 methyl groups. So if you had to guess and play in Mass Effect 2, if you had to guess, what would you call that? I'll give you a hint. The amide will be at the end. So it'll be amide. What would you call it? Good guess. Propyl amide. Sure. What else? Because propyl amide would work, but that only tells me that there's an amine in there and that there's a propyl group. So what else do we need? Methyl. All right, so now I know there's 1 methyl group. So how do I know that? How can I tell that there's 2? Dimethyl. Dimethyl propyl amide. See? We can name this before we even get the slides about the names. Always saying no. So negative. This is a nitrogen that has only had 1 functional group replaced with a hexane or butane. No. The name is slipping my mind at the moment. Benzene. A benzene ring attached to an amide. Benzyl amide. All right. So, like alcohols, but sort of reverse, we're going to classify our amines as primary, secondary, or tertiary.
Now we could have primary and secondary and tertiary alcohols, right? And what did those determine? How did you know if something was a primary versus a secondary versus a tertiary alcohol? What mattered? What mattered was how many carbons was the carbon that the hydroxyl was attached to, right? So the hydroxyl is attached to a carbon. How many other carbons is it attached to? If it's attached to just one, is it a single straight chain? Then it was a primary alcohol, right? If it was attached to one carbon that had two carbons coming off of it, like it was in the middle of something, then it was a secondary alcohol. When we're talking about our primary, secondary, and tertiary amines, though, what we're talking about is how many alkyl groups have substituted for the hydrogens. So a nitrogen is going to form 3 connections under its normal state. And so if you have one alkyl, then you are a primary amine. So this right here would just be methylamide. Because it's an amide, because there's an N, there's one alkyl group, it's a methyl group, so we're going to call it methylamide. Primary amide because there's only one carbon attached to that nitrogen. This is dimethylamide because there are 2 methyl groups attached to that nitrogen. That makes it a secondary amide because there are 2 alkyl groups. Doesn't matter what those groups are, just that there's 2 of them. This one on the end, that is a tertiary because it's 3-methyl or trimethylamide. Because there are 3 alkyl groups, 3 in this case methyl groups, attached to that nitrogen. Here's the space fill model of that, where we have our ammonia group. Now remember, this is pyramidal as opposed to tetrahedral, but that's because remember we actually have this electron pair up here that's kind of like taking up that cloud of the top of that pyramid, right? Making a little smiley face balloon, something. I don't know what that shape is. If we replace one of those hydrogens, we get our primary methylamine. Replace 2, we get our secondary dimethylamine. Replace all 3, we get our tertiary trimethylamine. What's the unifying part of all of these things? Aside from the fact that we're always adding methyls for this example because it's easier to draw and not have really small molecular structures, there's a nitrogen in the middle, right? That's what makes it an amide. There's a nitrogen there. So what do we name these guys? They have relatively simple names, just pretty much alkylamine, or alkylamide, alkylamine, so ethylamine, 2 carbon with an amine, dimethyl. Amine is 2 methyl groups with an amine molecule. Ethyl dimethylamine. Why is it ethyl dimethyl and not dimethyl ethyl?
Alphabetical. Okay.
Yeah, alphabetical. E comes before M. It's like, well, what about D for di? Like, yeah, that's a like, it's ethyl methyl. What comes first? E before M, right? If it was ethyl methyl propyl, it would come in that order. Ethyl, then methyl, then propyl. This is an amide with a benzene ring. As we learned when we first were introduced to benzene, we have a specific name for that. Just like benzene plus an alcohol is phenol, benzene with an amine group is aniline. So where do we start counting when we start talking about aromatic amines? You count with the carbon that is attached to the thing that makes it important, which is why the carbon right there is number 1, because that's the carbon attached to the amide. Attached to the nitrogen. Yes. The nitrogen is the thing that makes it important, so that carbon is number 1, which is why this is 4-bromoaniline. Because if that's the number 1 carbon, then 1, 2, 3, 4. The 4th one is where the bromine is attached. Now, remember before when we had esters, and we named esters based on what was on either side of the oxygen? We put it in alphabetical order, right? It was the thing that was earliest over here, then the thing that was next in alphabetical order, ether, right? We're going to name these amines in a similar fashion. When we're talking about something where we can't just put the nitrogen in the middle, for example, aniline is a specific amide compound that has, it's not benzene amide, right? It's aniline. So, if we're adding a methyl group, we can add it all over the place, right? We can add it up here, like we just did. Let's make this an obvious methyl group, shall we? CH3. There's the methyl group. What if I added it down here? What would that be instead? This is aniline, right? This right here is aniline. So what would this be? If we got rid of this carbon up here and just had that methyl group down there, what would it be? Just 3-methyl-aniline. Yeah.
So we get,
Because aniline is the name for that thing, right? We wouldn't call it benzenamide, right? It's aniline. Okay? So it would be 3-methyl-aniline. Well, we didn't add it to the aniline part, did we? We added a methyl group, but where did we add it to? We added it as a second component up there. Now normally, from the previous slide, we would name this as whatever this is, amide. Right? Or amine. Bromophenylamine or whatever, right? We would name it just like that. Ethyl dimethyl amine. Right? So this one here would be this thing, that thing, amine. Right? Except that this is an aromatic group. So the rule changes here. We're not just naming it around that. We now have a name for this right here. We call it aniline. So we know how to number things if we're attaching them to the ring, right? Just like this down here, 4-bromo. It's aniline with a bromine on the 4th carbon. So how do you name something that's attached up here to the nitrogen? This is N-methyl-aniline. That tells you that it's an aniline subunit, right? An aniline section. It's an aniline molecule. This right here, a hexagonal aromatic compound, benzene, with an amine attachment. We're going to call that aniline. But if you say N-methyl, that means it's aniline with a methyl group attached to the nitrogen. What would that be? What would you add to the name? Because it's still N-methyl-aniline, right? If we're going to have the long name, actually let's change this so that it's easier to say. Let's make this a 2-carbon chain, so that I'm not confusing 2 different methyl groups. What is that now? It's still N-methyl-aniline, but we need to add something else to it. What do we need to add? It would be, this is our first one, right? So 1, 2, 3. What is this? It's not a methyl group, it's a 2-carbon group. What do we call a 2-carbon group?
We call it, you need to erase the 3, and we'll be less confused.
You're right.
Butyl?
It's a 2-carbon group, not bute, that's 4. What's 2? ethyl. So it's N-methyl, 3-ethyl
Methyl.
aniline. Or actually, I think it would be 3-ethyl and methyl aniline. Because ethyl comes before methyl, alphabetically.
Wait, what?
This is 3-ethyl.
Right. Methyl.
N-methyl aniline.
You don't have to name the methyl coming off of the ethyl?
No, this is this is ethyl right here. That whole thing.
Oh, okay. Gracious. It's the 3, it threw me off. Sorry.
3, well that's because 1,
No, I got it.
3.
No, I meant the 3 subscript on the.
3-ethyl and methyl aniline.
Yeah. In the same way that if that methyl was over here, it would be, 3-ethyl, 5-methyl, right? But it's not on the ring, it's attached to the end. The way that you tell someone it's attached to the end is by saying it's attached to the end. It's N, whatever that thing is. In this case, N-methyl. I'm assuming that the chicken scratch of what's left behind when I erase is not actually that distracting as we move along. Is it easy to just kind of like let that fade to the background? Yeah? Yeah? Okay. Alright, so here are some amines that are drawn as a line format, line angle drawings. So they've named them for you, but try and name them without reading that. So how many carbons are in this first one?
4. 3.
We have that line right there ends in the NH2, so that's not a carbon. So we have 1, 2, 3. So it's a 3-carbon molecule, which makes it, so what's going to be in the name somewhere? Prop, right? But it's also an amide, so we're going to call it a propylamine, are we right? Propylamine. How about this up here? We have an N in the middle. So we've got, what do we have over here? We've got, is that a carbon right there?
No.
Nope. So we have 1, 2 carbon on the left. How many carbon on the right?
3.
1, 2, 3. So it's what? We have a 2 carbon, so we're going to need to have an ethyl in there somewhere, right? We have a 3 carbon, so we're going to need to have a propyl in there somewhere, right? What's the alphabetical order? E comes before P, so it's ethyl propylamine. Are we right? And they give us a note here, this is a secondary amine. Somebody tell me why? It's connected to 2 carbons. There are 2 alkyl substituents. There's the ethyl part and there's the propyl part. There are 2 carbon units attached to that nitrogen. That makes it a secondary. This last one's a tertiary. What would we call it? How many carbons right here? 2. How many right here? 2, and right here? Just 1. So this would be, we have a methyl group, and we have 2 ethyl groups. So what would we call it? Careful, diethyl. There's 2 ethyl groups. Diethyl, methyl, methylamine, right? Diethyl methylamine. Or Batman, sure. Or, see, when I look at that, and maybe this is just me, but I see the very first aerial unit from StarCraft.
I see Da Vinci.
Wow.
You see Da Vinci? Really?
That's flying machine.
Oh yeah.
Oh,
I see
yeah.
that. It's like, you say that and it makes you want to be like, I don't see how I can put the golden ratio here. It just doesn't work. Start drawing a circle around it. Yeah.
Wow.
They have it in StarCraft 2, the Wraith in StarCraft 2. They have it here. Alright.
You didn't say that one fine.
No, but that's a good show.
Yeah. Graphics here.
Graphics are horrible now. They're terribly dated, but it was good for what it was. Anyway, let's talk about the solubility of amines. Before you even read the slide, what are you going to guess? Are amines soluble, not so soluble? What do you think? Does ammonia dissolve in water? Yeah. So, if we add some alkyl groups to ammonia, do you think it'll dissolve in water? As long as we're not adding, as long as they're not very big, right? Same as with our alcohols and our carboxylic acids. As long as the alkyl groups that we're adding are not huge, yeah, because we'll have ammonia that can react with water. We can have the hydrogen bonding of ammonia. Primary and secondary amines with fewer than 6 carbons are soluble. 6 is about that number, right? 4 for alcohols when we start having problems. 5 for aldehydes and ketones when we start having problems. 6 when we start having problems with our carboxylic acids. And how about for amines? Once again, 6. When we get to 6, we're having trouble at 6, which means we're good up until 5. We start having trouble at around 5. They're soluble in water because they can form hydrogen bonds. Tertiary amines can only form hydrogen bonds with water molecules. Why is that? An amine NH, the NH bond in amines is polar. So it can form hydrogen bonds. The nitrogen is holding the electron density. So is it going to be partial negative or partial positive? The nitron's where the electron spends more of its time, and the electrons are negative. So the nitrogen will act just like the oxygen, right? It's going to be the negative part of the bond. The hydrogen is going to be the positive part of the bond. So why did it tell us back here tertiary amines can only form hydrogen bonds with water molecules? Because if we are tertiary amines, do we have any hydrogens anymore around that nitrogen? We have replaced all of the standard 3 hydrogens that ammonia comes with carbons on a tertiary amine, right? And so the only thing that's left is that lone pair, that partial negative of that lone pair. So primary amines can form more than one hydrogen bond because they have those extra hydrogens, right? Primary amines have how many hydrogens? 2. That's why it says primary amines can form more hydrogen bonds than secondary amines. Why? How many hydrogens does secondary amines have? Well, they take one of those 2 and you replace it with another alkyl, so they would only have 1. And so you still have that partial negative charge from the nitrogen, but you have 1 less positive charge from the hydrogen. So if we're decreasing the amount of things that water can hold on to, what do you think we're doing to the solubility of those molecules? We're reducing it. The more hands you have to play with water, the more water likes you. If we get rid of all of your hands, if you are not polar in any way, if you are not charged in any way, then water does not like you.
More like you don't have water, you're hydrophilic.
No, it's actually the opposite. Yes, hydrophilic means afraid of water, but the problem with the description for hydrophilic is it implies action on the wrong part. Oil is not afraid of water, so it runs away. Water does not like oil, so it kicks it out.
Okay.
The effect is the same. They separate. They are not miscible. They are not soluble. But it is not because oil doesn't want to hang out with water. It's because water kicks it out.
I said philic, I meant focus, sorry.
Yes, there you go. So, smaller amines, including even tertiary ones, are soluble because they can still form hydrogen bonds with water. But if we get too big, it's not. Amines with more than 6 carbon atoms, like this guy here, not going to be very soluble in water, are they? Because yeah, that nitrogen right there, it has that lone pair right on this side, which gives you a partial negative charge, so that you could have a hydrogen with a partial positive charge to associate with it to form a hydrogen bond. But if that's the only thing that water has to play with, and there's all that nonpolar stuff all around it, no sir. Water does not like it. by the way, slightly out of the box, but since we're on the topic, when you mix oil and water together mechanically by shaking it, they eventually will separate, right? Who's paying for that work? Because if I take a bunch of Legos and mix them together with a bunch of Duplos, which are not Legos, and then toss them on the floor, they're not going to just separate from each other automatically. I would have to get down on the floor or force my children to get down on the floor and physically separate them into their appropriate containers. So who's paying for oil to move away from water?
Well, you donated energy when you ship it.
I did, yes, but that energy isn't free. I donated it to force it to shake.
Right.
But that means it's not storing it. I used it to force them to mix. So getting them to unmix is going to take energy. Where's the energy coming from? It's the guy behind the curtain. Remember him?
Nobody likes him.
Nobody likes the guy behind the curtain.
Oh,
Entropy. Yes. Entropy doesn't like uncomfortable water molecules. And water molecules that are trying to hydrogen bond with this thing and can't, they're very uncomfortable. And so entropy will pay the bill to kick them out.
but by separating it physically like that, haven't you
Created a potential
formed
energy?
a potential energy because
Yes, to an extent you could say that I have, but that potential energy is going to come from entropy not wanting to leave it that way. Because one could argue that they're more chaotic that way. If I mix it all together, it should be more chaotic. And that would be true, except for the lack of hydrogen bond association with this long nonpolar molecule. And so entropy would actually prefer that they organize away from each other because it's a lower energy state, it's a more stable environment than leaving a bunch of water molecules around this nonpolar chain. It's entropy that's paying for that. So yeah, you could argue that by shaking it up I've created a potential energy situation, but it's not the same thing as, like, you can't tap into it, it's not like a battery. One could, but yeah, I mean, entropy is going to be paying for that movement. Like I
can
said,
I argue
that's-
that you prepaid for it?
No, it's hard. I think it would almost be semantics.
Okay.
A semantic argument. All right. Amines are a base. Why are they a base? Ammonia is a base. When we talked about Lowry acids, ammonia was a base. Why? Acids are by definition hydrogen donors. A base is a hydrogen acceptor. What does NH3 do in water? Does it donate one of those H's to become NH2 negative?
Yeah, hydrolyzes water.
It accepts hydrogen from water to become NH4 positive. And in this case, a hydroxide ion to keep everything balanced. Ammonia is a base. So what is ethylamine? Or methylamine in this case. Methylamine is a ammonia molecule, but instead of having one hydrogen, it's got a methyl group attached to it, right? Methylamine. But it's still got that nitrogen with that lone pair. It's still capable of absorbing a hydrogen ion, so it's still a base. So it can still absorb that hydrogen ion and leave you with a hydroxide ion. So amines act as bases, which implies something. What would you do to neutralize a base? You would add an acid, right?
Is that the trainer effect?
Trainer effect?
She's all about that base.
Oh, God. For a second, I thought you were being serious. I was like, wait, I'm unaware of this chemical phenomenon that you're attempting to reflect in your life. All right, so an amine salt forms when we react a basic amine with an acid, producing an amide salt, or amine salt. Amine salts do not have the same inherent chemical properties that amides do, that amine bases do when they become a base in a solution. The fishy smell of fish is because of the concentration of amines, in part at least. So the reason why, part of the reason why we sprinkle our fish with lemon juice or any other acid is to convert the amines, the basic amines that are in that meat, convert them into an amide salt, which keeps them in solution, which means we're not smelling them.
But doesn't it also pre-digest the meat some? It's already a very delicate flesh.
Adding a strong acid or a mildly strong acidic solution to fish, yes, is going to begin breaking things down. Sure. Yeah. It's nothing compared to your stomach acid once you start chewing on it.
Right. I was just thinking about how unpleasant marinating meats can make them with that outer layer of.
Because of the softness of it, as it softens the meat. Yeah.
Just citric acid.
Yeah. Or just acid digestion. So, how does that work? Here's our methylamine, which in water would form methyl ammonium, right? But if we take methyl ammonium and then add hydrochloric acid, that methyl ammonium is going to be positive, so it's going to react with the chlorine. How is this different than the carboxylic acid salts that we were talking about earlier? What did they react to? We neutralize them with bases. And we formed ammonium salts, right? Sodium salts, potassium salts, monosodium glutamate, remember that? It was bonding with the sodium part of that base. Well, now we already have a base, so we add an acid, and so it's going to bond with the negative part of that acid. So methyl ammonium chloride. This is dimethylamine. You combine that with hydrochloric acid, same deal. You'll get dimethyl ammonium chloride. The ammonium ion was the NH4. Did we say that all the way back here? Ammonia forms the ammonium ion. NH4 is the positively charged ionic form of an amine, of ammonium. Ammonium. That is why when we react it in water as a base, it becomes ammonium. But then you can make an ammonium salt by adding an acid to neutralize it. Methyl ammonium chloride, dimethyl ammonium chloride. So what would you name an amine salt? You would name it exactly what the amine was, except instead of amine, it's ammonium, and then what's the other thing it's with? Probably chloride. But you could do it with any other thing. You could do it with fluoric acid, bromic acid. Yeah. Methyl or dimethyl ammonium fluoride, or dimethyl ammonium bromide. Or dimethyl ammonium sulfate. Ammonium salts. We have to convert these amides to salts in order to precipitate them. Just like we had to convert our carboxylic acids to salts in order to precipitate them. Sudafed, Benadryl, ammonium salts. Solid at room temperature, odorless and soluble in water, and therefore deliverable in body fluids.
Aren't those also smelling salts then?
I am not certain what smelling salts are. I thought those were just ethers. No, they wouldn't be ethers because that would knock you out, not wake you up. So I don't know what I'm not certain what smelling salts are.
Ammonia inhalants.
So it's just ammonia?
Oh, it's ammonium carbonate.
Right. All right. Medication, ammonium salts. This is ephedrine hydrochloride, otherwise known as Sudafed. Here is our amine right here.
So where's the ephedrine part?
What?
Ephedrine hydrochloride. Because ephedrine as an amine is going to have how many hydrogens? Amides will only have how many things attached to them? 3. If they have 4, that makes them the ammonium part, right? So why did I draw this line here? Because that H right there is the thing that makes that positive charge. This nitrogen, when it is neutral, would have how many things attached to it? 1, 2, 3. Everybody see it? The 4th thing attached here is the hydrogen to make it ammonium, and then the chlorine to make it a salt. So ephedrine hydrochloride. Next time you're looking at ingredients or chemical names for your things, like when you're looking at like your cough medicines, you'll notice that there's a lot of stuff that's like that. Something or other hydrochloride. Now you know why it's named. Like, why are they giving you this medicine along with this acid hydrochloride? Well, this is why. Because the way they made it precipitate so that they could put it into a pill instead of being something that you necessarily drank as a liquid was by making an ammonium salt out of it. And then we named it the specific molecule plus HCl. The H made it the ammonium, and then the chlorine makes it the salt. Diphenyldramamine hydrochloride. Do you see the phenol? Do you see the diphenol? What's phenol? A benzene ring plus an OH, right? Where's the diphenol? It's got a diphenol right there. Dramamine, so there's that plus the amide right there plus HCl. Diphenyldramamine. You're not going to be expected to name molecules like this. I just want you to be able to recognize where that name, like what does that name referencing? That's Benadryl. That's the thing that'll knock me on my butt for about 4 hours. If I take that to help me sleep, don't even try and wake me up before 4 hours. I will not get up. 6 hours I can get up and not function well. I don't like Benadryl. Just a personal thing.
Take it every day that goes away.
Mm-hmm.
But then it's also been linked to early onset of dementia.
Lovely.
Someone didn't.
All right, how about cocaine?
How about it?
Extracted from coca leaves using an acidic hydrochloride solution.
Back in-
It's smuggled illegally in the form of cocaine hydrochloride, which is an ammonium salt. So here is cocaine hydrochloride, because there's the ammonium right there. Here's the ammonium. So we have all this stuff down here. That end is connected to one connection here on that ring, 2 connections there on that side of that ring, 3 connections here to that methyl group, but then that 4th one, that's the guy that brings in that positive charge right there. And here's the chlorine that makes it a salt. You react that with sodium hydroxide, and all of a sudden that sodium is going to scavenge that chlorine, right? To make sodium chloride. That hydroxyl will scavenge that hydrogen to make water. And what are you left with? Instead of the hydrochloric salt of cocaine, you just have cocaine. You are now prepared to help out drug cartels in some South American country or something. I don't know. They probably already have people who know how to do this. They seem to be pretty good at it. This is not me in any way endorsing a life of selling illegal drugs.
What?
A meth slide.
Oh, I thought you said it's more of a lifestyle. First, I get no kick from cocaine.
Cocaine hydrochloride, which is the ammonium salt, you can convert it back to the free amine or base form. And that gives you the solid cocaine. And if you crystallize that, you can get crack. Crack cocaine. Which is just, it's rock sugar made out of coke. It's rock salt. Sugar. We were just talking about this earlier.
No, baking soda.
No, the bath salt.
No,
Not rocks.
not rock salt.
Sugar.
Sugar salts, the sugar salt candies that I was complaining nobody should ever buy.
Yeah.
Rock
Rock
candy,
salt.
it's rock candy. It's rock candy made out of cocaine. That's what I'm looking for. Like, it's just a different, instead of a powder, instead of salted and powdered, it's just the solidified crystal. It's still just cocaine. The thing that made crack so bad is, because how do you, like, okay, because I watch TV, I know this. How do you normally take cocaine? It's a powder that you sniff, you snort it. In other words, you shove it up your nose, and why would anyone in their right mind do that? I don't know. But the point of doing it is the same reason why Flonase is something you inject into your nose. The point of doing it is because you have mucous membranes up in your nose that can absorb that chemical into your bloodstream relatively quickly. It's certainly a lot faster than taking a pill. Shots actually are incredibly fast, but they're also dangerous because shot puts it directly into your bloodstream. Strong concentration. Your nasal passages up here, your moist nasal passages, allow for relatively fast absorption. Guess where you can get even faster absorption? Only below injecting.
Upper palate.
Your respiratory system.
Oh, yeah.
You've got a little bit of surface area up here in your nose where you have live cells that can absorb chemicals. Where can you find a crap load more surface area of live cells whose job it is to absorb stuff? In here. The reason crack cocaine was so bad, twofold. One, because it was absorbed into the bloodstream faster. And two, not to be racially insensitive, but two, there was a specific ethnic group that tended to use crack cocaine. And at the time that it became really, really bad, the US government was, let's just say, racist. So, crack was bad because African Americans did it. Coke was okay because white people did it.
Coke and Coca-Cola.
Yeah, I don't know about that. But,
No, they didn't.
Back in the,
but originally,
Yeah.
first Coke and Coca-Cola?
Yeah.
It's like, I don't know. Okay. Point is, there's no real difference. The thing that made crack bad was the rate at which it was inhaled. But that wasn't the reason why it was criminalized to the degree it was. It was criminalized because of, let's just call it social issues.
Oh, yeah, that
The
was
war on
advent of
drugs.
The war on
Yeah,
drugs.
exactly.
Yeah.
Yep. The thing
The
that
program
started.
that most successfully expanded drug use and
And the privatization of our criminal, of our,
and
of
yeah,
our
and
jails.
imprisoned a whole
imprisoned, right.
group of
A generation or two. Yes.
Americans.
Weed's legal
What's that?
there. Weed's legal
Not
in
really.
certain states.
In certain
It's
states.
not federally, so it's not.
Yeah, there's a small handful of states where it's legal, but here's the thing. It is still illegal at the federal level, which means the federal government can come in and arrest you whether the state says it's okay or not. And they can charge you in a federal court.
they can still take away your,
You get fired.
As long as you have
still take away your student loans as well.
Yeah, because it's federal, yeah, it's a federal thing. So yeah, there are places where it's legal and everybody is just like, you guys, you feds are cool with this, right?
Jurisdiction.
Yeah, pot plants stuff. If you got two,
It's
in
legal in
California,
Colombia
you
with a
got
lot of
two pot plants.
stipulations.
But
It's what?
It's legal in Colombia with a lot of
so we
stipulations.
Really?
You can have up to 35 grams, but if any officer has jurisdiction outside of Colombia, then those municipal, well, no, not the municipal, but the state regs still apply.
Right, yeah, so they get arrested there.
So like an MU campus police officer, which is a subdivision of State Highway Patrol, they can arrest you all day long, charge you, convict you, and you lose your student loans.
But the city cops,
Yeah,
well, under a certain way.
yeah,
Right.
I was unaware of this.
yeah.
All right, on the subject of alkaloids.
You bored? No.
On the subject of alkaloids, an alkaloid is a physically active compound that's produced by plants that contains a nitrogen. So it's relevant to our current conversation because we've been talking about amines, right? And what are amines? Biological molecules with a nitrogen in them. So alkaloids are nitrogen-containing compounds that come from plants that are biologically, aka / psychoactively active. Anesthetics, antidepressants, stimulants.
Poisons.
Alcohol is a poison, my friend.
No,
Caffeine.
but just an unreasonably large percentage of our common poisons are plant-based alkaloids.
Yes, which is one of the reasons why when somebody says, here, take this, it's natural, it's perfectly safe. I'm like,
Yeah.
really? I have some belladonna you can chew on, you're going to have fun with that.
I've had that, and a doctor prescribed it. Just saying.
Belladonna?
Yeah.
Yes.
For beauty treatments?
No.
No,
Because
you're
there's
thinking of
only-
Botox.
I get severe sleep deprived when I was pregnant, and they prescribed me that while pregnant because it doesn't cross the,
Yeah, interesting.
To
The,
do
And-
what?
for sleep, because
Oh,
I
as a
won't
depressant.
sleep forever. And, I was hallucinating berries and stuff.
wow,
Belladonna.
that was some good stuff.
Tomatoes.
Must be,
Which herbal remedy shop did you get that from?
No,
I
right.
believe tomatoes and potatoes are both in the belladonna nightshade family.
They are, the nitrate family, yes, yep. Which is why and that's an aspect of why they're the devil's fruit, tomatoes.
Devil's fruit.
Vegetable.
Devil's fruit, yeah.
They're devil's vegetable in the United States.
Yeah. Nicotine. Here's nicotine. Here's a stimulant that increases the level of adrenaline in the blood, increases your heart rate, your blood pressure, but is also rather addictive. Nicotine. So here we have a nitrogen-containing phenol ring attached to this ring here. This ring does not have double bonds in it though, so these carbons right here specifically are free to bend up or down. But all of these guys and that guy right there are going to be planar. But the moment you start moving into the rest of this ring can be like odd angles because of the way carbon works.
Aren't you real close to serotonin then?
You are.
Stop.
Here's caffeine. Lovely, lovely caffeine. An alkaloid found in coffee beans, tea, chocolate, and anything else we shove it into, which in America is a lot of crack.
And it's more addictive, if you look at it compared to certain drugs and the addiction, it's way up
Oh, yeah.
there.
Like,
Way up
I
there.
am addicted to Mountain Dew, and I know that I'm addicted to caffeine, but it's like it's Mountain Dew specifically, because I'll walk, like I was with a friend at Hy-Vee last night, and we walked by one of those cases with all the sodas in it, and I just saw the Mountain Dew, and I was just like, like, and not the Cokes or the Dr. Peppers, couldn't carry less, but the Mountain Dew. So it's like when you feel that like longing for something that is missing in your life, like that's just you're
It's
addicted
like up
to
there
it.
with heroin.
It feels like teachers and Mountain Dew, because every science teacher I've ever had loves Mountain Dew, buys it by the gallon.
It's
If
nerds.
they could.
It's nerd culture and caffeine culture. Yeah.
Oh, sorry. Can't program without code.
See, well, that you are you from further east of here?
I know I'm from Los Angeles, Steve.
Really? Because that's the other thing is we are close to St. Louis here, and so I had a friend who's from St. Louis, and St. Louis and east, kind of like east and a bit south, I think, so kind of like southeast of St. Louis. Coke is the word. Like if you walked up to a
Yeah, everything is.
and just say I'd like a Coke, they'd say, well, what type? And they don't mean diet.
Yeah.
Like you could say I'd like a Coke, and what you mean is Dr. Pepper or Mountain Dew, because that's the instead of soda or pop.
That's why they say
So,
Coca-Cola.
That's how
Coke,
South
Coke, yeah,
Dakota
yeah.
is, everything's a Coke. I want a Coke.
Yeah, want a Coke? Yeah.
In Texas, it's Dr. Sell Dr. Pepper.
On the subject of Coke,
Yeah.
And caffeine.
In the South, everything's Dr. Pepper. Like all my family in Alabama,
You wanna
it's
have
Dr. Pepper.
Yeah.
Everything is Dr. Pepper.
It's the way
Dr. Pepper, the best thing about Dr. Pepper is plum juice, which makes it a drink for warriors. Worf told me so.
A warrior's drink.
Exactly.
Oh my goodness.
I'm gonna just
The
date
sad
myself with
thing
all
is,
sorts of
is I
sci-fi
never
references
worked
while I'm
in
here. Why
caffeine
not?
anymore.
Alright,
It's
so
like peptide cake.
here's the thing about caffeine. Caffeine is one of the only things that has actually been shown via scientific evidence to have a improvement effect on our intelligence and alertness. Well, alertness, there are other things, but intelligence. Caffeine is one of the only potential psychostimulants that can actually improve your intelligence. The problem is it comes with drawbacks. And it's not by a significant amount, but it is one of those things where if you study while highly caffeinated, you should test while highly caffeinated.
That makes a lot of sense.
I should do that.
I should.
This is not me condoning overexposure of caffeine. I'm just telling you there's some research related to this. Caffeine is an alkaloid. It is a hydrocarbon with a lot of nitrogens in it. It's also, one of the reasons why it has an effect on alertness is because if you take a look at this and then overlap the shape of adenosine, which is the same A that you find in ATP, the same A that you find in DNA and RNA, it has a very similar shape to adenosine. And the reason why it stimulates our awakeness is because caffeine, as an adrenergic agonist, will activate the same receptors in your brain that adenosine does. And so it is hijacking the way that your brain normally tells itself, it's time to wake up, by artificially increasing something that looks like adenosine in your brain noggin.
Can you say that one thing again? It's not on the slide.
It's time to wake up.
Agonist?
Adrenergic agonist.
Oh,
It is
adrenal.
an agonist to the adrenergic receptors, not adrenal adrenergic receptors.
Can you say that 3 times fast?
Agonist for the adrenergic receptors, agonist for the adrenergic receptors, agonist for the adrenergic receptors.
Okay, yeah.
Ask and you shall receive. Increases alertness, but may cause insomnia. And if you're addicted to it, it will not keep you from sleeping, it will just keep you from getting any benefit from sleep. I can drink a Mountain Dew at 1 a.m. and go straight to bed. I will pass out. Problem is when I wake up at 7 in the morning, I will be tired as... I'll be tired.
Can't drink caffeine after 5. Coffee.
Yeah, see, I have no problem going to sleep. It's just that the sleep that I get is crap. So, I'm aware of this, but sometimes, like tonight, when I'm having to work on your guys' test, probably won't matter. So, let's talk about some more alkaloids. Amine compounds in plants. Morphine and codeine. Alkaloids obtained from oriental poppy.
Sorry.
Here's morphine. Hydroxyl's over here. Here's codeine, where we methylate that hydroxyl.
Has that been cut or is it really just sweat up even with that?
I don't know. I do know that the poppy has seams on it, so it probably just sweats it. I highly doubt that that's been cut. Now, I don't think that there's much that you can do about that as far as getting high by just taking that syrup and like licking it. But if we purify it out for those chemicals, that is where it comes from. Is that right there?
Well, if you just reduce the moisture content, it becomes opium, I believe.
I don't know. I'm unaware of the distillation process of purifying these alkaloids from the sap of the poppy plant. I do know, with some anecdotal evidence, that there is something to be said about poppy seed muffins
Yes,
causing problems
it does.
with drug tests.
Yes.
Yep.
I can see that.
You
Yeah.
can pay your drug test.
Don't
Declare
eat
it.
poppy seed muffins. if you're
Don't eat poppy seed muffins right before you take a drug
You
test.
can as long as you declare it.
Or
Yeah,
drink
you just tell them,
fruit
I just had like 30 poppy seed muffins for
Yeah,
breakfast.
A shot of heroin.
There might be a limit to the believability of that. Like anything more than 3, I'm not buying it.
It takes one muffin to totally throw off the test though.
Aw.
Well, can't you drink like prune juice and other stuff like that
Oh, yeah.
to clear it out of your system?
I I don't know about opioids,
I thought it
but
was cranberry.
there's stuff you can do for marijuana that helps.
Alright, so, amides. Tylenol contains acetaminophen. It has reduces fever and pain, but doesn't have an impact on inflammation. And there's a reason for that, the difference between Tylenol and aspirin. And it has to do with which enzymes it is blocking. But that goes much deeper than what we're going to be worried about in this class.
Where does paracetamol come from? Is that just a brand name? It's like Tylenol?
It might be, I'm not familiar with it.
It's the UK thing. That's what they call it. I don't know.
So, amides, as opposed to amines, forgive me, I've been putting a D in there when I shouldn't have been earlier. Amides are derivatives very similar to our esters. What's the difference between the amine and the amide?
D.
Thank you, yes, the presence of a D, which has been slipping in just like I's, but it shouldn't have been. This is still an amine right here, right? This would be a primary amine, because it's a nitrogen connected to one carbon, right? But this carbon has a double bonded oxygen. In other words, it's not just an amine connected to an alkene or an alkane. It's an amine connected to a carboxylic acid. So, this is ethanoic acid. This is ethanamide. Ethanamide, ethanamide. Because we have that double bond right there.
Did you have the double bond on
Not in the amines, no. If we go back to our amines here, that right there is connected to carbons that don't have double bonds immediately next to them. This guy right here, no double bond immediately next to them. These are your amines as opposed to your amides.
Mine's the double bond of oxygen.
Right, just like an ester. It's the difference between an ester and an ether, that double bonded oxygen right next to it. An amine versus an amide. An amide has that double bonded oxygen right next to it. It replaces the hydroxyl group of a carboxylic acid group, which means we can talk about how to make them. So, we can take propionic acid and react it with ammonia. The thing they didn't circle here is, what does that make? Water, so it's a condensation reaction. So we're replacing the hydroxyl and that hydrogen, popping them off and putting an amine functional group next to it, which makes it an amide molecule because you have the amine right next to the double bonded oxygen. So you get, instead of propamine, you get propamide. Same idea down here, propanoic acid and methylamine instead of ammonia. We're doing the same thing. We are reacting that hydrogen, we are replacing that hydrogen right there on the amine and the hydroxyl in the carboxylic acid to make water, just to keep up that same pattern. And we're getting a methyl propamide, but where is that methyl attached?
To the nitrogen.
It's attached to the nitrogen, thus the N-methylpropamide. Now what this is telling you is, if we're attaching a methylated amine or an alkylated amine to a carboxylic acid, by definition, what is that going to result in? An N something or other amide. Everybody see that? This CH3 could be replaced with R, which is just R group or side group, just any alkyl group. That could be a methyl group, it could be an ethyl group, it could be a 3,4-dichloropenthyl group. And what we're going to get is N, whatever that thing is, and then that amide. Everybody follow? Because this is the carboxylic acid. So that's the name of the amide.
propamide. Propamide, right? It's the carboxylic acid, just like when we were talking about esters. The thing that gives you the main name, in other words, the last word in the name, that's the carboxylic acid, right? Methylpropanoate, right? It's the carboxylic acid that makes that last part of the name. But if we're attaching any sort of alkylated amine, and what does alkylated amine mean? What's an alkylated amine? It's an amine with alkyl substituents. What's an alkyl substituent? Everything we've been talking about for the last 3 chapters. A methyl group, an ethyl group, a 2-dichloryl propyl group. Anything that is a hydrocarbon or a modified hydrocarbon, that's an alkyl group. So an alkylated amine is an amine with carbon things attached to it. If we're forming an amide by reacting a carboxylic acid and an amine, then you're going to get an N attachment. By definition, you're getting a molecule with an N attachment. I might be spending too much time talking about this. It's not that important, but it's a pattern that I like to point out. Once again, how do we name them? We name them where the last bit is the important stuff. So once again, like I just said, when we're naming esters, the last word is going to be based off of the carboxylic acid, right? When we're naming amides, the last word is going to be named after the carboxylic acid. The previous part is going to be named after the amide. So this is dimethylamine, N-N-dimethylamine, because both of them are attached to the N now, right? This was just dimethylamine before, because the amine part of the name told you that you had 2 methyls attached to the N, right? Well, now when we have this big dimethylamide butanamide, we need to know where those methyls are attached to. And in this case, they're attached to the N. So, how would it be different if this was 3-methyl, 3N, 3 comma, or it might be N comma 3. Dimethylamine. We would still have a methyl butyramide down here, right? But if it's 3N or N3, I'm not sure which one comes first off the top of my head. I don't remember that name, that rule. Well, that tells you that one of those methyls is N attached, right? So it'd be here, but the other one would be where? Where's the 3rd carbon? Is it here? 1, 2, 3? Would we go like that? 1, 2, 3. So it would be attached here. Everybody follow? The N is just the way that we know that we're saying we have a attachment right there. Now, once again, this would be different because this wouldn't be butyric acid anymore. What would it be? It would be 3-methyl butyric acid, right? Combined with, and it wouldn't be N-N-dimethylamine anymore. It would just be, well, it'd just be methylamine, right? If it was just these 2 right here, it would just be methylamine instead of dimethylamine. Name that. First off, what's special about it? We see an N, right? So that means it's either going to be an amine or an amide. What's the difference between an amine or an amide? Because both of them have an N. The double bonded oxygen right next to it, right? So, this is an amide. What's the longest chain, or I should say, what's the chain, which side of this was the carboxylic acid side, the left or the right? The left, because that's the one with the most oxygens, right? It's still that same thing. This over here was the carboxylic acid side. So, the last part of the name, actually let's do it the way they do it, because they're probably going to do it with the prefixes first. It's an amide. We know it's an amide because of this right now, right? So, what's the substituent attached to the amide? That right there. So we're going to have a methyl part, right? But it's not just going to be methyl, it's going to be what? Where's the methyl attached? Is it attached to the second carbon, the third carbon, the first carbon? It's attached to the end, right? So what's this going to be? N-methyl, right? Oh, dagnabbit, now they're doing it the other way. N-methyl. See, I was right. Now let's go back to this. Where did they get butanamide? 1, 2, 3, 4. So the carboxylic acid that we started with was a 4-carbon carboxylic acid. So it's butane. It's butanamide, right? So that's the butanamide portion. And then we have the methyl part that's attached to the N, so it's N-methyl butanamide. Now remember, these slides that are asking you to name stuff are easy because they're smack dab in the middle of the chapter where we're talking about amines, right? But in a test question, it's not going to be that way. It's going to be, here's a molecule, what's the name? Pick from these 4 or 5 options. So what are you going to do? If it's just straight C's and H's, then this is easy, right? You just count carbons, find the longest chain, blah, blah, blah. But if there's anything else, if there's any oxygens in there, where are they? Are they single bonded oxygens? Are they double bonded oxygens? Is there an N in there? Where is it? Is it next to a double bonded oxygen? Find the thing that makes it special. That tells you what, whatever the at the end is. Amide, butyric acid, whatever, right? How many can we fit into one sentence? Where do these amides come into play? In biological synthesis, in biology, in biochemistry. Urea is one. See here we have 2 amines, 2 amines, excuse me, attached to a carbon with a double bonded oxygen. So this is a double amide almost, isn't it? Because we have our amine attached to a carbon with a double bonded oxygen. That's urea. The kidneys malfunction, that builds up in the blood, and it starts to crystallize in your joints, in your blood vessels, all over the place, causing all sorts of problems. A lot of barbiturates are just cyclic amides of barbituric acid. So here's phenobarbital, or pentylbarbital. Here's the pheno part of the phenobarbital. Here's the pento, 1, 2, 3, 4, 5, right? Pento part of the pentobarbital. That is a ring structure of nitrogens connected to double bonded carbon oxygens. Double bonded oxygen carbons, that's better. Amides, not amines, amides. What do barbiturates do to us? Depressants, drugs, psychoreactive drugs. Aspirin substitutes, acetaminophen down here. A nitrogen attached to an acetamide. Here we have a carbon with a double bonded oxygen, 2 carbons. Phenol group there.
Phenacetin? Same deal. Double bonded oxygen connects to a nitrogen.
Not amines, but amides. All right, so if we can make them in a condensation reaction, we can break them in a hydrolysis reaction, just like esters. Same thing. If we do acid hydrolysis, we make the carboxylic acid again and an ammonium salt. So here we have ethanamide, which is a ethanoic acid combined with just amine, right? It's ammonia. Put that together with heat, with a little bit of water to get our hydrogen or hydroxyl and some hydrochloric acid in heat, and we get our ethanoic acid again and ammonium chloride. N-methylpropanamide. Propanamide. That tells you that's the acid. So what's that going to be converted into? Propanoic acid, right? And so our N-methyl means that we had a methyl group attached to the nitrogen. So we turn that back into an amine, and what are you going to get? Instead of NH3, you're going to get NH2 plus that methyl group, right? And whatever it is, that's still going to be attached to that nitrogen, right? We're going to break the bond between the double bonded oxygen carbon and the nitrogen. Can we zoom in on that a bit? Sure, just a second. We're going to break this bond and recreate the acid on the left and then the amine on the right. So we're still going to have a methyl amine after we break that apart, right? Except that if we're doing this in a base, instead of recreating the carboxylic acid as a full acid, we're creating our carboxylic salt. We're creating it as the ion, which is why this isn't propanoic acid, it's propanoate. Sodium propanoate. But it's the same thing, just instead of recreating the acid, we recreate the salt. You just have to remember the difference. Or know how to look it up. Draw the condensed structural formulas for the products of the hydrolysis of N-methylpentanamide with sodium hydroxide. So what's N-methylpentanamide? Well, we know we have a methyl group, right, attached to the N. Well, sort of. You're thinking of cyclopentene. But you're right, it's going to have a 5 carbon. That's what pentanamide means, is 5 carbon. So, we're going to have a methyl group attached to the N. And on the other side, we're going to have 5 carbons. And where's the double bonded oxygen going to be? On the methyl group or on one of the carbons with a 5? On one of the 5 carbons, right? Specifically the number 1 carbon, because that's why we count, that's where we start counting from, right? So, here's our methyl, here's our N, here's our carbon with a double bond, and 1, 2, 3, 4, 5. Is that what you had pictured in your head? It's certainly what we described, right? So this is N-methyl, right there, pentanamide. An amide of that group right there, because of those guys right there, 5 carbons on the left. We're reacting this with sodium hydroxide. So, that hydrogen is going to go down here to our amine, creating what? What's a nitrogen with a single methyl group attached to it? What do we call that? Methylamine. Not methylamide. That was my mistake earlier. Methylamine. Because there's no double bonded carbon, no double bonded oxygen to a carbon anymore, right? And then we're not combining it with a OH down here, we're combining it with an O and a sodium. So we're not going to get pentanoic acid, are we? What are we going to get instead? Sodium pentanoate. Sodium pentanoate. It's the pentanoic acid, but instead of having the hydrogen, we have the ion with sodium attached to it. Did everyone follow that? Try to? Alright, so, believe it or not, we just made it through chapter 14. Good thing, bad thing. Good thing is, we made it through.
Less question, but more stress.
Which means we can put it on the test, because we finished it. It also means that I have more work for me to do tonight. Because I need to actually finish that chapter to put it on the test. The first three are already there. It also means that the homework that I also have to make tonight, or tomorrow morning, is going to be over both chapter 13 and 14, instead of just chapter 13.
What's the test over?
Test is going to be over chapters 11, 12, 13, 14. It should open tomorrow at 8. It closes when?
Sunday.
Sunday at midnight. I should say it's due Sunday at midnight, right? So as long as you start it, I think start it before midnight on Sunday night, you will get full points for whatever it is that you're doing. How much math should there be in this? Like, oblique, use your calculator math? Not much to pretty much none. Like, exceptionally simple type math. There may be some balancing of equations that might require a little bit of really basic math, but you're certainly not going to be doing any sort of like long division or balance, you know, figuring out where what goes divided by what in an algebra, anything like that, right? Which is good if you don't like math, bad if you, because it means that you actually have to know more about what you're doing instead of being able to just apply equations. I'm afraid those are long past us.
I'm trying to think of when we balanced the equation, was it chapter 11 or 12?
The combustion of hydrocarbons. Yes.
Okay.
There may be questions that ask you about, say, what's the coefficient in front of this part of this equation, that type of stuff. Balancing equations, right? So that's still a thing in these chapters. Not so much in like how do you name an amide, because we didn't really talk about the combustion of those. But back when we were first talking about beginning alkanes, yeah, combustion of those guys. All right, any other questions? If you don't finish it by Sunday, it will remain open, but you will take a 10% penalty for any day that you are late. I think everybody took it on time last time, so that's good. If we can do that again, that'd be awesome. As soon as everyone is finished, I will go back in and open and change the view again so that you can go in and see what your answers were, right? It will still automatically grade, so the moment that you're done and hit submit and save, you'll know how you've done.
Oh, good, it's all multiple choice.
Yeah, multiple choice, true, false. Yep, there's not going to be any short answer or anything like that.
Will the last one be the same way?
Yep. Yeah. The only difference about the last test, if that's what you mean, is that the last test you won't have a grace period for lateness.
Yeah.
Because I have to submit grades by Tuesday morning. So
We don't have a homework, right? On week 8 or do
you do. Yes, there will still be a homework that will be due on Thursday, week 8. Yes. But there will not be a new one that opens that you only have 2 days to finish. So there will be a homework due the last week. But there will be a new one opening with a test the last week, just because of the way it overlaps. So we don't have to worry about that. So we're almost done with our homework. We're almost done with the class. We're 3/4 of the way through. So, hope you guys learned something. Anybody have any more questions about material tonight, or do y'all just want GTFO?